solve for the location of the stress at any point using this equation. All right, but in order to determine our location of our maximum stress, we still need to solve where our angle is. So we know that where our neutral axis is. So we can determine the neutral axis relative to the the y, z coordinate system using this formula here. So we get it would be equal to this tangent beta would be equal to this equation on the right hand side here. All right, so all those values are known values. These are all known, so you can plug them all in and you can solve directly for beta. If you solve directly for beta, you get 33.4 degrees, which again it would be equal to alpha plus theta p. So it's the same value obtained in the other method. Okay, so once you have that, you could then identify the 2 points. So at point A, you would just plug in the values of you would just plug in the known values into the sigma x equation to solve for sigma x, and you can do the same thing at point B, and you'd end up getting the same stresses. Okay, so these are the same results as the ones we got before. So either method is fine, whatever is most convenient for you to use. All right. And then, so then the last part of the problem is to find the deflection at the free end of the cantilever beam. Okay, so for a cantilever beam, all right, where we have a force being applied, all right, at the end of a beam, we know that the deflection at the end of the beam is equal to the force times the length cubed divided by 3 times the moment inertia times the elastic modulus. All right, so what we first do is we need to rewrite our applied force that we had in our problem in terms of the m and the n directions. Okay, so we know what theta p is equal to, and we know what Fy is equal to, and we know what Fz is equal to. So I think Fy, if I recall correctly from the problem, is I think it's equal to minus 2,000 or minus 3,000. Yeah, it's equal to minus 2,000 newtons, and Fz is equal to 0 newtons. So we're going to convert those into, we plug those in, we can solve for Fm and Fn. All right, and then the only thing, so then all you need to do is you just need to use this delta equation for both the m axis and for the n axis, and we're going to find our deflections about the m axis and the n axis using these two equations. Okay. The one thing that I'd like to note here is that when you're using these equations, make sure that you use the correct moment of inertias and the forces. So the force should always be in the direction of the deflection. So in this case, we have our deflection is about the m-axis and our force is about the m-axis, while the moment of inertia is about the axis that is perpendicular to the deflection direction. Okay, so we have n here corresponds with m, while m here corresponds with n here. Okay, so make sure you use the correct one, otherwise you're going to get the incorrect answer for your deflection. So once you have, so you can just values in that equation are known, all right, from earlier in the problem. So you just have to plug them in, solve for these two equations, and then the last part is that you can determine the deflection in the YZ coordinate system. You just have to plug in to this equation here, and if you did all of that, what you'd end up getting is minus 11.27 millimeters, and then for the displacement on the y direction, and 17.10 millimeters for the displacement along the z direction. Okay, you can plug in either delta m and delta n, or delta y and delta z into this equation here to find delta max, which would be equal to 20.5 millimeters. Okay. All right. So, that is the end of the problem. Does anyone have any questions regarding? I guess there was a lot to the problem. All right. So let's just go back and look at the original problem statement here. Okay. Okay. So in this problem, we were able to find the bending stress, okay, at a given point, all right, based off of the loading that was shown in our diagram. Once we we could then we're able to calculate our neutral axis to identify what points in our along the cross-sectional area would undergo our maximum and minimum bending stresses. We then did solve for those maximum bending stresses. We then showed how we could use the direct equation to solve for the angle beta to find our neutral axis. And then once we had, we could then solve for directly the points that were undergoing the maximum and minimum stresses using the y and z coordinate system. And then the last part was we had to then solve for the deflection of this section, for this cantilever beam section, using the following two equations here. Using the deflection equations. And once we were able to do that, we solved for delta m and delta n. We converted those to delta x and delta y and delta z. And we could also then solve for the maximum stress as being the square root of the sum of the squares.